Welcome to this explainer. Today we're doing something a little different. We're going to look right past the daily grind of debugging and syntax errors to examine the actual master blueprint of software development. We're stripping away all that heavy framework-specific jargon to look at the universal journey that literally every piece of code takes. We're focusing on the core architectural concepts that every single programmer relies on to build the digital world around us. I want you to think about this for a second. Every app on your phone, every website you visit, every video game you play, no matter how wildly different they might look on the surface, they are all built on the exact same foundational concepts. It's true. From that initial spark of an idea, all the way down to the massive databases storing your high scores, there is a universal journey that all software takes. So, what exactly is that journey?
Okay, let's dive into our roadmap for today. We'll be exploring how software gets made, talking to the machine, directing the traffic, organizing your code, and finally, storing the data. Let's get into it.
Section 1. How software gets made. The big picture.
A lot of people think creating software just starts with a programmer frantically banging away on a keyboard in some dark room, right? But actually, scratch that. It really starts with a carefully constructed plan. This is known as the Systems Development Lifecycle, or SDLC for short. Notice how it's a circle? It's a continuous loop. System analysts rely on this exact loop to map out the inputs, the processing, and the outputs of a system way before a single line of code is ever written. It's basically the big picture view of an application's entire lifespan. Stepping through these 5 critical phases, it all kicks off with planning and analysis, basically figuring out what the software actually needs to do. Then, the architectural blueprints are drawn up in the design phase. Phase 4 is implementation. Now, this is the magic moment where programmers finally sit down and start writing the code in a specific language. And finally, there's maintenance, where developers repair, update, and tweak the software over time. And hey, once the software becomes obsolete, the whole cycle just starts all over again. Moving on to Section 2, talking to the machine, interpreted versus compiled. Okay, so once we hit that implementation phase, we run into a pretty major challenge. How do human programmers actually communicate instructions to a computer's silicon hardware? Because at its core, hardware only understands machine code, just ones and zeros. To bridge this gap, we use programming languages, and these generally divide into 2 main translation camps. First, think of interpreted languages kind of like a live UN translator. They translate the code line by line, right on the fly while the program is running. It's super portable and makes finding errors or debugging really easy, but it can be a little bit slower. On the other hand, compiled languages are more like a fully translated book that was published ahead of time. The code is entirely pre-translated before it even runs. That makes it incredibly fast and catches errors early, but it's usually tied to specific hardware. So how does this actually play out in the real world? Well, if you're doing quick web development or scripting, you're absolutely going to love interpreted languages like Python or JavaScript. But if you're building a high-performance video game or an operating system, you're going to rely on the blazing speed of compiled languages like C++ or Rust. And of course, there are hybrid languages too, like Java and C#, that use techniques like just-in-time compilation. They basically try to give developers the best of both worlds, balancing that flexibility with speed. Which brings us to Section 3, directing the traffic, the grammar of code. All right, we've picked our language to talk to the machine. Now we need actual grammar to build logical steps. And this brings us to a massively important concept called control flow. This is simply the order in which statements within a program execute. Now sure, the most basic programs just run straight top to bottom, completely sequentially. But you know as well as I do, the real world isn't sequential. Programs have to be flexible to handle dynamic, totally unpredictable real-world tasks. That means we have to move way beyond a simple top-to-bottom flow. I mean, think about it. What happens when a program needs to make a choice based on what a user types? Or what if it needs to process a massive list of, say, 1,000 different items? It can't just read straight down a simple list of instructions. It needs to adapt, branch out, and loop back. To handle this traffic, developers use 3 main types of control flow statements. First up are conditional statements, like your classic if-else commands. These act as the decision makers. If the password is correct, log the user in. Else, show an error. Pretty straightforward. Second, we have looping statements, like for or while loops. These let the program repeat an action over and over, maybe iterating over every single element in a giant list. And finally, jump statements, like break or return. These are super handy because they allow a program to suddenly exit a loop early or just jump to a completely different part of the code.
This right here, this is the true heartbeat of software logic. Section 4, organizing your code, programming paradigms.
So, it's one thing to write a few loops and conditionals, but modern applications have literally millions of lines of code. How do developers prevent massive projects from turning into an absolute tangled mess of chaos? They use programming paradigms. The two biggest philosophies here are procedural programming and object-oriented programming. Procedural is the older style, used a lot in languages like C. It works top-down, kind of like a step-by-step recipe that divides the program into small functions. It's great, but the data isn't highly secured. Then you have object-oriented programming, or OOP, used in languages like Java and Python. OOP works bottom-up. It organizes code into objects that contain both the data itself and the actions you can take on that data. It's highly secure and allows developers to reuse code like self-contained real-world Lego blocks. If you're designing massive, complex programs, OOP is an absolute game changer.
So, the crucial point is, we now have a beautifully organized, perfectly logical piece of software. But logic alone isn't enough, is it? When you update your profile picture, or hit save on a new high score, or add a cool item to your shopping cart, where does all this code actually store its information so it doesn't just vanish into thin air when you close the app?
That brings us to Section 5, storing the data, the vaults. You see, databases are essentially the digital vaults of the modern world. Without them to manage and retrieve data efficiently, our software would have total amnesia every single time we turned it off. Broadly speaking, there are two main types of vaults. First, relational databases, which use SQL. These are highly structured. Think of them like massive, incredibly strict spreadsheets with perfectly organized tables, rows, and columns. They are absolutely perfect for things like banking and structured data. On the flip side, we have NoSQL databases. These are highly flexible and store unstructured or semi-structured data, like JSON documents or key-value pairs. And because they scale horizontally so incredibly well, NoSQL is the absolute go-to for handling massive, unpredictable data volumes, like, say, a global social media feed.
Now, in dealing with those strict relational databases, developers rely on 4 foundational pillars known as the ACID properties: atomicity, consistency, isolation, and durability. Let's use a bank transfer as a quick example. Atomicity guarantees that a transaction, like moving money from your savings to checking, either completes perfectly in its entirety or it doesn't happen at all. No half-finished transfers. Consistency ensures that data stays perfectly valid. Isolation means millions of people can do transfers simultaneously without crashing into each other. And durability? That means that once a transfer is complete, it is saved permanently. Even if someone literally trips over the cord and pulls the plug on the server, your money is absolutely safe.
And there you have it. You now understand the complete journey, from planning out that system's development lifecycle to choosing exactly how to talk to the hardware, writing the logical control flow, organizing your code blocks, and finally, securely storing all that data in a digital vault. You have the universal blueprint that powers the entire digital world. So, my final provocative question to you is this: what kind of application would you build right now with this blueprint in your hands? Think about it. Keep exploring, keep learning, and I'll catch you in the next explainer.